Howdy class. So today I'm going to talk to you about something called polyatomic ions. So we've talked about ionic compounds and we've talked about molecular or covalent compounds, but polyatomic ions are ions that are composed of covalent bonds. So these are multi-atom or polyatomic atom or polyatomic ions. So we have more than one type of atom making up these ions. And I've circled / put boxes around the ones that I think are particularly important for you to remember. These are the ones that'll come up a lot. Not that you won't see the other ones, but I won't make you memorize the other ones. I will definitely make you memorize most of these. So ammonium ion, NH4+, hydroxide ion, OH-, cyanide ion is Cn-. The acetate ion, which I will almost always write as CH3COO, and that's one of those structural formulas that I mentioned briefly in my previous video that tells us about the connectivity of the atoms. So the acetate ion actually looks like this. It's got a carbon with 3 hydrogens on it, just like it says here, attached to another carbon, which has 2 oxygens. And then that oxygen has a minus charge, -1 charge. All right, so there's also the sulfate ion, like copper sulfate, for example, is something composed of sulfate. There's phosphate. So one of the chemicals that I worked with extensively in my research was silver phosphate. So I am a big fan of the phosphate ion. There's also the nitrate ion. I also worked a lot with silver nitrate, so another big fan of the nitrate ion. And then these two you won't see as often, but they might come up, is the chlorate or perchlorate ions. And those we'll talk about in a few slides. Those are unique because they have just differing numbers of oxygen. So those are called oxoanions, and we'll talk about those in a little bit. The carbonate ion, that one is pretty good to remember because you'll see sodium carbonate or sodium bicarbonate, which is this one down here, which is baking soda, sodium bicarbonate. But carbonate you'll see a good number of times. Calcium carbonate is lime. It is basically what makes up limestone. And then another fun one to remember, this one's not as important to remember, but it's a fun one, is the permanganate ion. That one makes a solution that is bright purple, which is pretty fun. Alrighty, so when we're making ionic compounds using these polyatomic ions, we're going to use kind of the same system that we use to make the formulas for the other ionic compounds with monoatomic ions. So ionic compounds have a formula containing a certain number of cations and anions. We always write the cation first, and that is just the name of the metal, pretty much. And our charges have to add up to 0. So this is the formula for calcium phosphate. Calcium phosphate is in your bones. This is the formula for calcium phosphate. So the subscript tells us that it tells us the number of calcium ions. The subscript over here tells us the number of phosphate ions. So remember, this whole thing is one ion. So that is the same way that we had like calcium chloride before. If we had calcium chloride, now we're putting a polyatomic ion in there. So that polyatomic ion has to stay together, and that's why we use these parentheses when we're writing polyatomic ions with subscripts. So I'll erase that so you can see the parentheses better. So that means there are 2 phosphate ions in this molecular formula. So we need the parentheses around it, because if you don't have the parentheses, it's going to look more like calcium with a subscript of 3, and then PO42. And that's not what we want. We don't want 42 oxygen atoms. We want 2 phosphate ions. Okay, and that's what the parentheses are for. They're very important. So how do we know that this is the right formula for calcium phosphate? Calcium is in group 2A, or 2, as we write it now. So that means it has a +2 charge, as we see down here. Phosphate is a polyatomic ion with a -3 charge. So you're just going to have to memorize those, unfortunately. So I'll go back to that slide. Phosphate is right here, has a -3 charge. So you're just going to have to memorize what the names of the ions are and what their charges are. They're always the same. They don't change. These polyatomic ions always have the same charge. That is written here in this table. Anywho, phosphate is a polyatomic ion with a -3 charge. To make the neutral compound, we need 3 calcium ions and 2 phosphate ions. So this is kind of the same thing that we did with the aluminum, what was it, aluminum, I don't remember what it was. Aluminum oxide, I think, in the ionic compounds slides. So now we've got calcium, 2+, and phosphate, which is PO4, 3-. So we do our little squiggly arrow thing, and that's going to be the subscript for our phosphate. So you got to put it in parentheses. So there's a 2 with the calcium, so now there's a 2 with the phosphate. Then we take our 3 and we put it with our calcium. Boop. So we just do the same thing with the charges and the subscripts that we did before. If you need to check, which you should always check, you can do that. So the subscript, the 3, times the charge on calcium, +2. So that gives us a +6. The subscript, which is 2 on the phosphate ion, times the charge on the phosphate ion, which is -3, gives us a -6. And if we add them together, we've got +6 -6, we get 0. Perfect. That's how we check to make sure that we have the right formula for our ionic compound. All right, let's practice. So you guys can pause it here and practice on your own if you'd like, but I'm just going to go through the answers real quick. Hopefully you got them. So barium is in group 2, so it's got a 2+ charge. Sulfate, one of our polyatomic ions, has a -2 charge. So we got barium and we got sulfate, and they cancel each other out. So we got +2 and -2 gives us 0. So we only need 1 of each. So we don't need any subscripts, we don't need any parentheses, because we only have 1 of each. All right, what about this one? Ammonium ion, NH4+, and chloride ion. So we got a +1 and a -1. So those are the same as our barium sulfate. We just put them together. So we've got a +1 and a -1. Oops. -1. So we get another 0. So that is our neutral compound, ammonium chloride. We don't need any parentheses or any subscripts on our ions. The subscripts are going to stay there that are part of the polyatomic ion. We're not going to take those away because that is an entity on its own. It keeps the subscript because that is the definition of the ion. All right, let's try a different one. We got sodium and carbonate. So carbonate has a -2 charge and sodium has a +1 charge. So we're going to need 2 of those. So we'll have sodium with a 2 and carbonate. So that means we have 2 times +1 and -2. So that's +2 -2 equals 0. Perfect. So you can do that with the little arrows if you want. So the charge on carbonate goes to the subscript, and the charge on sodium goes to the subscript, but we don't write ones, so we don't need a subscript for carbonate. And because we don't need a subscript for carbonate, we don't need parentheses. Cool. And last one, magnesium and the hydroxide ion. So OH minus is hydroxide. All right, so magnesium has a 2+ charge. It's in group 2. And hydroxide has a 1-, so it's a minus charge. So we're going to do the opposite of what we did with the previous one. We're going to do magnesium, and we're going to have 2 hydroxides. So we took our 2, we put it in the subscript. Took our 1, we don't write the subscript, but it's kind of there, it's implied. So we've got a +2 plus 2 times -1 gives us 0. So note this time I needed parentheses because magnesium hydroxide, oops, is not the same as saying magnesium OH2. They're very different. One exists and one doesn't really. So this is how we have to write it, not like this. We need our parentheses. All right, awesome. So what else can we learn today? So I mentioned these briefly. Oxoacids, or sorry, I mentioned oxoanions. So oxoanions are all of those polyatomic ions that have different numbers of oxygens. So when we add hydrogen to them, they become oxoacids because if you remember on our previous set of slides, we learned that anything that gives off a hydrogen ion in solution, it dissolves and it gives off a hydrogen ion that makes it an acid. So if we add hydrogen to any of our polyatomic oxoanions, they become oxoacids because if we put them in water, they would dissolve and give off that hydrogen that we put on. All right, so they differ only in the number of oxygen atoms. Then the naming pattern is the same with oxoacids as it is with polyatomic oxoanions. So we have this nice little chart here. This is from a different book, but I like it. So this little chart here can help you remember what the proper name is for the ion or the acid. So down here, we have, these are the chlorine-based ones. We've got perchloric acid, chlorous acid, and hypochlorous acid. These are the bromine-based ones. We've got perbromic acid, bromous acid, hypobromous acid, and these are the iodide-based ones. So periodic acid, iodous acid, and periodous acid. These are not the only ones. We also have oxoanions with nitrogen and sulfur. And I guess we have some with phosphorus as well. So let's take a look. I'll show you how to use this little graphic here. So for example, I'm going to start with the 8. So the 8 is kind of the basic one. That's the one that I told you to remember for everything: phosphate, nitrate, sulfate. So I'm going to start there. So I'm going to do it with the chlorine-based ones though. So chlorate is ClO3. And we get that, so that's the oxoanion. You can see it down here if you look at what's attached to the hydrogen. So the oxoanion is attached to the hydrogen. So ClO3 minus is our chlorate ion. If we add another oxygen to it, so we get ClO4, that is the perchlorate ion. So that's ClO4 minus, so the charge doesn't change, but the number of oxygens does. We take an oxygen away instead, and we get the chlorite ion. So that's ClO2 minus. If we take one more oxygen away, we're going to get the hypochlorite ion. So that all of those are on our polyatomic ion list. So we've got perchlorate, chlorate, chlorite, and hypochlorite. And the acids that are formed from these oxoanions are called oxoacids, and they have different endings a little bit. So when we have the perchlorate ion, we have perchloric acid. So perchloric acid is down here, HClO4. And now it's neutral. Now we don't have a charge because we got a positive hydrogen ion attached on there. So we have perchloric acid. Chloric acid is just HClO3. We take away another oxygen. We've got HClO2, that is chlorous acid. And we go one more and we've got hypochlorous acid. So the ones to remember really would be chloric acid and chlorate ion go together. Chlorous acid and chlorite ion go together. So the ic and the ate ending go together. The us and the ite ending go together. And then the hypo is the same and the per is the same. So that is how you use this little graphic if you want to remember how to name oxoacids or oxoanions. So if you remember, so say all you remember is that this is the chlorate ion. You don't need to remember that it's called chloric acid if you remember how this chart works, I guess. And you don't need to remember that this one is perchlorate as long as you remember that when you add an oxygen, it becomes perchlorate or per-ate. So it could be per-bromate or per-iodate, whatever. The base part stays here. So chlor for chlorine, brom for bromine, and iode for iodine. All right, so you guys can study that as much as you need to. I don't know that I will actually ask you to memorize that, but here it is. You might need it in your homework. Anywho, keep going on. So what else is there in chapter 5.7? We've got hydrates. So hydrates are a hydrated ionic compound. So what does that mean? So ionic compounds like, I'll go back to my friend copper sulfate. So copper sulfate is a hydrated compound. That means that there is water trapped within the crystalline solid, within the lattice of copper sulfate. So we talked about how all ionic solids have this lattice energy. They've got different ions kind of all spaced out in their structure. Like this. I'm not a good artist, but they've got lots of different ions. Well, they've got the same ions. So say this is, the big ones are copper and the little ones are sulfate. It's got alternating copper and sulfate ions forming a lattice or a ionic solid. And it's not just copper and sulfate ions in there. For copper sulfate, there's actually water trapped in that solid. And the water that's associated with the compound is called the waters of hydration, and it's included in the molar mass. So, for example, if you are working in the lab and you need reagent grade, so the kind that you would buy from a supplier, You'd buy from a chemical supplier, you'd buy copper sulfate. You wouldn't get just copper sulfate. The reagent grade copper sulfate that's provided will be the hydrated compound. It'll be copper sulfate pentahydrate. So we're going to use those prefixes that came up in the covalent compounds. We're going to use those prefixes with our waters. So pentahydrate means there's 5 waters associated with the copper sulfate molecules. So for every 1 copper sulfate molecule, there are 5 waters associated with that copper sulfate molecule inside of the crystalline lattice. So when you're calculating the molar mass of the copper sulfate pentahydrate, this is something that we'll get to in the next set of slides for Sunday. But if you were calculating the molar mass, how much 1 mole of copper sulfate pentahydrate weighed, you couldn't just use the mass of copper sulfate. You would need to include the mass of those 5 waters in the molar mass. And we can actually find out what's a hydrated compound, how many waters are associated with 1 molecule of the ionic compound. We can find that out by heating the hydrated compound to release the water from the crystalline solid. So you heat up the compound until the water evaporates out of the ionic lattice, and all you have left is the copper sulfate or the other ionic compound. All you have left is that with no waters associated with it. So you have to do something chemically, physically in the lab to get rid of those waters. So copper sulfate by itself, not really a naturally occurring compound. You have to heat it up to get rid of the waters. So you'll always find it. If you found copper sulfate in nature, it would be the hydrated form. So if you heat up 1 mole of copper sulfate pentahydrate, you would end up releasing 5 moles of water for every 1 mole of hydrated compound. And I found a cute little graphic that shows that pretty well. So this is a little video that someone put together. When you heat up copper sulfate, which is blue, it's a pretty blue crystalline solid. If you heat it up, it's going to lose the waters of hydration, and it's going to become white copper sulfate crystals. So copper sulfate without any waters is actually white. It loses all of its blue color. And we call this copper sulfate without any waters of hydration, we call it anhydrous white copper sulfate, or anhydrous copper sulfate. So we don't need to worry about the numbers in this process, but I can show you this little video for fun, maybe. Maybe not. There we go. So this is what's happening in the crucible as it heats. You can watch the blue color disappear. It took about 10 minutes heating over a Bunsen burner to get rid of the waters of hydration. And you can see, you don't have to worry about it mathematically right now. We will get there though. You can see that we had an initial mass of 0.1859 grams, and now we have a mass of 0.1188 grams. So we lost, I don't know, about 0.7, 0.6 or 0.7, sorry, 0.06 or 07 grams of mass that was in the water. So the water evaporated, so we can't get the mass of it anymore because now it's in the atmosphere. So the difference in the mass here is the mass of the waters that were evaporated. Pretty cool, right? Okay. All right, and just to finish up, chapter 5.7, your book gives you this little table of some common ionic compounds that you've probably heard of before for at least most of them. Of course, there's water, ammonia, Ammonia is in like a lot of cleaning solutions. You might have heard of it before. Dry ice, if you've seen any cool science demos, they usually use dry ice. Or if you've gone to any theater productions where they have a smoke machine or a fog machine, that uses dry ice, which is solid carbon dioxide. Sodium chloride is salt. It's the normal table salt. Nitrous oxide is laughing gas, which they use at like some dentist's office, I think. Calcium carbonate, like I said before, is limestone. Here's our sodium bicarbonate, I said before, is baking soda. And then a couple weird ones with magnesium. We have Epsom salt and milk of magnesia, which you might have heard of, but you might not have, because those are kind of older, more herbal remedy type things for different diseases or injuries, or, you know, just whatever. So you might have heard of those, you might not, but these are the common names in the middle here. And then the systematic name, which is the naming system that we learned, the nomenclature that we learned in this chapter for those compounds, and their formulas over here on the left. Cool. So I'm going to just give you one summary slide. I'm not going to talk about this one, but this is a summary of how we name cations: monoatomic cations, transition metal cations, monoatomic anions, polyatomic ions. So this doesn't really tell you much about how they're named for polyatomic ions, just that we add ion on the end. So this is the hydroxide ion, for example. And then ionic compounds, we put those two ion names together. The first one, the cation, goes first. It stays the way it's written. So sodium, iron, ammonium, they just stay like that. And then the second one has the "ide" on the end. So hydroxide, chloride, whatever. So this is an example for ammonium hydroxide, which is two of our polyatomic ions combined. So ammonium and hydroxide ions to make ammonium hydroxide. All right, I'm going to break here, go to another video.